Welcome to Mac TV with Professor V. In this video, we're going to look at extra examples of how to switch a Cartesian integral to a polar integral and then evaluate it. If you need a video lecture on polar integrals, I'll link it in the description, but I'm just going to continue and do some extra examples that I worked on with my class this week. So here the problem says, change the Cartesian integral to an equivalent polar integral, then evaluate. And if you notice, if we were to try to do the integral directly, it would be oh so nasty, right? Look at these limits of integration. Look at the function that we're integrating. Yuck. So nowhere did it say graph, but you have to graph. And what are we graphing exactly? We're going to graph the integration region, namely in the xy plane. So let's figure out what this region, what these bounds are representing. So notice, we're integrating with respect to x last. That means the limits -3 to 3 are my limits for x. So x goes from -3 to 3. And then similarly, the limits for y are from negative rad 9 minus x squared all the way to positive rad 9 minus x squared. Hopefully you recognize right off the bat what both of these functions represent the equation of. If not, I'm just going to remind you quickly. So we know x squared plus y squared equals r squared is the equation of a circle centered at 0, 0 with radius r. If I solve for y, I get y squared equals r squared minus x squared. And so y is plus or minus square root r squared minus x squared. And you should have kind of this picture in your head. The positive radical represents the upper half of this circle. That's the positive rad. And then the negative radical is the bottom half of the circle. Okay? Now, similarly, had I solved for x in terms of y, you would end up with x equals plus or minus radical r squared minus y squared. And then what that does is break up your circle into the right and left half, which is another way we get things done around here. So then the positive radical would be the right half of the circle, and then the negative radical would be the left half of the circle. This is going to come up so much throughout the remainder of the course, so just put it to memory. That way you can, proceed quick as a bunny through the problem. All right, so I'm going to graph the integration region in the xy plane. I'm not graphing a 3D graph at the moment. No. I'm just graphing in the xy plane what these limits of integration are bounding, okay, what the region is. So x is going from -3 to 3. Okay, and then y, the upper bound is the upper half of a circle whose radius is 3, and the lower bound is the bottom half of a circle whose radius is 3. So these are the bounds for y, and then these are the bounds for x all the way from -3 to +3. So it looks like we're integrating over this entire circle whose radius is 3, yes, centered at the origin. So our goal now is to switch to a polar coordinate system. So we have to figure out what the limits of integration would be for r and for theta. Well, since we're tracing out the entire circle, theta is going to start at 0 and go all the way to 2 pi radians, right? We're covering the entire circle here. So theta starts here at 0, swoops out, always counterclockwise, and we're going to go all the way to 2 pi. So theta goes 0 to 2 pi. Now r is going to start from 0 and go all the way to 3. A few students of mine got a little confused and they went from -3 to 3. That's not correct. Why? Well, if theta is going all the way from 0 to 2 pi, then r only needs to go from 0 to 3 in order to trace out this entire integration region. Also, when figuring out the limits for r, I'm going to show you a trick later on. Start from the center of your region, start from the origin, and then just draw a line going out. Where it starts is the lower bound, and then where it hits is the upper bound. And this equation is r equals 3, right? If we switch it to polar. This circle's equation is x squared plus y squared equals r squared, right? Which is 3 squared. So we have r squared equals 9, and we don't put plus or minus 3. We just usually write r equals 3. Okay, so it looks like we're ready to switch to polar. I'll say 99% of the time, theta is the last variable that you integrate with respect to. So your limits 0 to 2 pi go on the outside. Later, once in a while, you do r last, but not too often, okay? So I'll put 0 to 2 pi out here. Then r goes from 0 to 3. And then notice here, we got to change our function. So 1 plus x squared plus y squared, that's going to be 1 plus r squared, squared in the denominator. And then we replace dy dx, which is dA, with r dr d theta. Okay, so just a quick recap. If you're in rectangular, dA can be dx dy or dy dx. If you're in polar, it's r dr d theta or r d theta dr. Less often. More often it's this guy. Also, just in case you forgot, x is r cosine theta, y is r sine theta, and then x squared plus y squared is r squared. All right, fabulous. Now let's look at this integral. What's the nicest way to evaluate it? Well, my eye is going to the fact that all of these limits of integration are constants. Fabulous. So that means I can break it up because notice here my integrand, it's just a function of r. I don't even see any thetas. Whew. So split it up and watch this. So I can write this as 0 to 2 pi. Those are the limits for theta. So d theta, you go there. Ba-boom. Times integral 0 to 3, and then I'm left with r dr over 1 plus r squared squared. Nice, right? Don't use this trick unless all the limits are constants, and then your integrand can be broken up as a function of r times a function of theta, or whatever variables you have here. Okay. Now let's see. This integral 0 to 2 pi d theta just ends up being 2 pi. Is that obvious to you? If not, we'll work it through really quickly. There's no function, it's just a 1, right? So antiderivative would be theta that you would evaluate from 0 to 2 pi, which would be 2 pi minus 0. So when there's no function, just a d theta or d whatever, you take the upper limit minus the lower limit, and that's what the definite integral ends up equaling. So we don't need to put all this. We know now this is just going to be a 2 pi, and then we carry on with our life. 2 pi times the integral 0 to 3 r dr over 1 plus r squared squared. Now how would you evaluate this? Well, I notice in the denominator I have 1 plus r squared, and then I have r to the first, 1 degree lower in the numerator, so it's a perfect time to do u sub. So let's let u equal 1 plus r squared. Then du is going to be 2r dr. What's in my integral? Just r dr. So that means 1/2 du is r dr, which I have right here. Also, we need to change our limits of integration. So u of 0 is 1 plus 0 squared, so that's 1. And then u of 3 is 1 plus 3 squared, which is 10. Okay, so now let's see what we've got. We have 2 pi integral. Instead of 0 to 3, we're going from 1 to 10. This r dr in the numerator, I'm going to replace with the 1/2 du. 1/2 du over, and then it's 1 plus r squared is u, and that's all squared. Okay, so this 2 out here cancels with the 1/2. And then, oh, I need a bit more space. Please bear with. Let me add myself a little page. Let's rewrite. We have pi integral from 1 to 10. U squared in the denominator means we have u to the negative second, and then du. Okay. Just because you see something in the denominator doesn't mean the antiderivative is going to involve ln. I see that little oops all the time, okay? So rewrite it, it's u to the negative second, and then add 1 to the exponent, divide by the new exponent. So we have pi times u to the negative first divided by negative 1, right? From 1 to 10. So I can take out negative pi, and then I have u to the negative first. So that's going to be 1/10 minus 1. That's giving me negative 9/10 times negative pi is positive 9 pi over 10. And that's the answer. And we are done. How was that? I think the trickiest part is drawing the integration region, switching the limits of integration to polar. It's not, you may erroneously think all I need to do is just say, oh, well, you know, x is r cosine theta. I'm just going to sub it in. So, no, certainly not. That's not how it works. So you have to draw. Did anyone tell you to draw a graph? No, but that's how you have to solve it. There's no weaseling your way out of that one, you know? Okay. Let's move on, because the more examples you have under your belt, the better shape you'll be in. 0 to natural log of 4, 0 to rad ln of 4 squared minus y squared, and then here's the integrand, e to the rad x squared plus y squared dx dy. Okay, so again, let's graph what's going on. The limits for y, notice here's dy on the outside, so these are the limits for y. They go from 0 to ln of 4. The limits for x go from 0 to rad ln of 4 squared minus y squared. Do you recognize what this represents the equation of? Yes, it's the right half of a circle whose radius is natural log of 4. Do you remember I showed you that earlier? It's okay if you forgot. Here, x equals plus or minus rad y squared minus r squared minus y squared. This is the right half of the circle. Okay. So we're good. Can you draw the right half of a circle whose radius is natural log of 4? Don't get nervous about the fact that the radius is, you know, ln of 4. It's probably going to be something you're grateful for later. You just go, well, this feels like a nice place to call natural log of 4. This will be negative ln of 4, you know? Yes, Professor V, this all looks fabulous. Okay, so x goes from 0 to ln of 4. This is 0 right here. Okay, all the way to ln of 4. And then this is interesting. Y goes from 0 to ln of 4. So y goes from 0 to ln of 4. So I'm not going to shade this whole thing. No, we're starting at 0 all the way up to ln of 4. So it looks like we've just got a quarter circle this time, right? That's fine. So tell me, what would the limits for theta and r be if we're going to switch this to a polar integral? So theta, only quarter circle. Theta starting from 0 and going all the way to, this is pi over 2. And then r starts at 0 and goes outward. What is this? This is the radius of the circle, which is just natural log of 4. So 0 to ln of 4. Okay, do you feel ready? Let's switch this guy up. So let's do theta last. That's typically how it works. 0 to pi over 2, then r, 0 to ln of 4. Then let's look at the integrand. E, this is rad x squared plus y squared is rad r squared, which I'm just going to replace with r. So e to the r. And then remember, dx dy, we replace with r dr d theta. Don't forget that extra r. Okay, I'm looking through. I don't see any thetas, so I'm going to do the same little shortcut from last time. And in fact, all of this is just going to go away. Imagine if I broke it up separately, and then I'd end up with an extra pi over 2 outside. So I'm just going to skip to that. Pi over 2, 0 to ln of 4, r e to the r dr. And now I'm looking, oh, it's time for integration by parts, right? So we have to pick u and we have to pick dv. If you have an exponential function, usually that's what you're going to let be dv, e to the r dr, and then u is just r. So du is dr, and dv will be, excuse me, not dv, oh my god, v. V will be e to the r. Good. So then we have pi over 2 times uv, so that's r e to the r. Remember, that's evaluated from 0 to ln of 4 minus integral 0 to ln of 4 v du, which is e to the r dr. Can you do that integral? I certainly hope so. Yeah. Pi over 2 times, I'll evaluate everything in the next step. So r e to the r minus, this antiderivative is just e to the r, and then we're going from 0 to natural log of 4. Okay, let's see. Pi over 2 times, this is ln of 4 times e to the ln of 4. Oh, now it's making sense, right? How nice that we have ln of 4. Upper limit minus lower limit, 0 times e to the 0 minus e to the 0. Okay. E to the ln of 4, that's just 4. That's just 4. So what do we have going on? Pi over 2 times 4 ln of 4 minus 4 minus 0 plus 1, right? Yes, good, Professor V. You're doing a nice job. Oh, thank you, everybody. Okay. So pi over 2 times, we have 4 ln of 4 minus 3. Et voila. Beautiful. You feeling better? Yeah, I hope so. Okay, this next one you're going to like. I like it. Integrate f of xy equals ln of x squared plus y squared over x squared plus y squared over the region 1 is less than or equal to x squared plus y squared is less than or equal to 4. Ooh, they didn't tell me whether or not I should use polar, but I mean, come on, look at it. It feels like we would want to do polar. Let's graph the integration region. So x squared plus y squared equals 4. That's a circle whose radius is 2. And then x squared plus y squared equals 1 is a circle whose radius is 1. So here's a circle, radius 1, and then here's another circle, radius 2. And my integration region is between and on the border of those two circles. So this is the region we're integrating over. It looks like a donut. That sounds good. Maybe I'll go get one. It's very early over here, so I have time. Okay. Yeah, it seems like a perfect time to go polar, right? Come on, people. So what should the limits for theta and r be? Well, let's see. Theta goes all the way around, right? 0 to 2 pi. Now what about r? Let me erase this. Again, I told you, start from the center, draw a line out. Where it hits first is the lower limit. Where it hits second is the upper limit. Well, it's going to go from 1 to 2. That might have been obvious without drawing the line, but you'll see. I'm going to do another example where you're going to be grateful that I taught you about this little line method. You're like, oh, thank you, Professor V. Okay. Do we feel good? I feel great. Let's set this bad boy up. So 0 to 2 pi, 1 to 2. Change the function to polar. So ln of r squared over r squared times r dr d theta. First glance, I see no thetas. I rejoice. And then I quickly say, well, that means I'm going to slap a 2 pi out here, right? This is, oh, I meant to do highlighter. That was so aggressive. Okay, this all gets replaced with 2 pi. Boom. Like, you instantly feel better now when you have a single integral, right? Isn't it calming to the soul? Okay, then we have 1 to 2. Notice this r can cancel with one of those down there. So then I have natural log of r squared over r dr. How to proceed? You will do a u sub. The easiest u sub comes after applying log properties. So there's more than one way to do this, okay? But I'll show you the cleanest. Don't forget, this exponent I can move to the front. of my logarithm and write it as 2 times natural log of r. You can go straight to the u sub without doing this, but I think it's a little bit easier. So we have 1 to 2 natural log of r over r dr. Do you see now who to let u be? Yes, u should be ln of r, because then du is 1 over r dr, right? How fabulous. And then let's change our limits of integration. So u of 1, that's my lower limit, would be natural log of 1, which is 0. And then u of 2 is ln of 2, which I just leave as is, okay? Great. So now we have, let's see, I mean, there's no reason why these two should not be joined outside the integral together. 4 pi, look at them having a party out there. From 0 to ln of 2, ln of r is u, and then 1 over r dr is my du. Oh, beautiful. Beautiful. Okay, antiderivative of u, 1/2 u squared. So 4 pi times 1/2 u squared from 0 to ln of 2. So then I have 2 pi times natural log of 2 squared minus 0 squared. And then this is just 2 pi times natural log of 2 squared. No, that exponent cannot move to the front. Were you wondering such a thing? Allow me to remind you about your log properties. Ln of a raised to the b, yes, it equals b times ln of a. Because the exponent, that b, only applies to the argument a. But ln of a to the b, stop. Leave as is. Nothing more can be done. Do you see the difference? Okay. Be a careful mathematician. Okay. Now, the other thing that happens is you have to do polar areas. So I have a couple examples, and I have other videos with this, but since I'm making this video for my students. If other people find it beneficial, fabulous. We did this in class this week, so I wanted to give them some solutions. Okay, so it says, find the area of the region specified in polar coordinates. And we are in Calc 3, so we're not going to use the polar area setup that a Calculus 2 student uses. No, we're going to use a double integral. So when you set up an area problem in Calc 3 with a double integral, you just have double integral dA. There is no function. And I had a discussion with my class earlier. So count up how many actual little integrals there are. That will tell you about the dimension. So there's 2 of them. That's a double integral. 2 dimension means I have an area. Also in Calc 1, you learned area integral f of x dx. Well, why was that? Because this is the height, and then this together, dx with the integral, gives you the base. So it's 2 dimensions. One for the integral, 2 dimensions for the base. If I gave you like a double integral and you had a function, dA, what would that represent? So you have 1, 2, this is 3. This would be a volume. Do you see the difference? Also, you could get a volume if you just did triple integral and then you had dv and there was no function. As soon as I add a function, now this integral represents a 4-dimensional quantity. So just keep track of what's going on. It's an area if you have a double integral dA and no function. As soon as you slap a function in there, now it's a volume. Or you could do triple, no function, that's also a volume. You see? Okay. So we're setting it up this way. We have to find the area of the region enclosed by the curve r equals 6 cosine theta. If you need a little polar review, ooh, I got you, okay? I have a whole video reviewing polar graphs. I'll put it in the description. But basically, r equals a, that's a circle, centered at 0, 0, and the radius is a. If r equals 2a cosine theta, that's a circle centered on the x-axis. So the center would be at a comma 0 and the radius is a. And then if you have r equals 2a sine theta, that's again a circle centered on the y-axis, so at 0a, and again, the radius is a. I'm telling you this because these kinds of circles come up so often. You don't want to sit there, be that sad little schmuck in class who's like making a table just to get a little circle on your paper, you know. It's going to come up a lot. You want to save some time so you can get to the beefy part of the problem. All right, so can you recognize, 6 cosine theta, that's a circle, centered on the x-axis, and the radius is 3. It's always half of whatever that number is sitting out there. So let's graph it. Centered on the x-axis, radius is 3. Let me put a circle here. Wow, beautiful. Okay, and we want the area of this entire circle. Okay, great. Okay. So let's figure out, we're gonna use a polar integral. What should the limits for theta be, and what should the limits for r be? Well, look at theta. Theta starts, where does the area start? It starts down here, and it swoops all the way up to here. So it's going to go from negative pi over 2 to pi over 2. If you did 0 to 2 pi, that would be wrong, because 0 to pi over 2, we have area. There's no area here. So if your integral covers a region where there's no area, it's going to give you incorrect values. Then the area picks back up from 3 pi over 2 to 2 pi. So if you were to split it 0 to pi over 2, 3 pi over 2 to 2 pi, that would be fine. But why would you set up two integrals if you could just do one clean one from negative pi over 2 to pi over 2? Yeah? Okay, and then what about r? This is when my little trick where I say draw a little line segment is helpful. Start at the origin, swoop it out, okay? Lower limit is 0. That's where the area starts. Upper limit is, it's not going to be a constant, right? See how this length changes depending on where I am? But it is determined by the equation of the circle, which is 6 cosine theta. So r goes from 0 to 6 cosine theta. If the circle is centered at the origin, then r is going to go from 0 to whatever the radius is, a constant. But when the circle is not centered at the origin, it has to go to whatever the circle's equation is. Okay, are we ready? Yeah, okay, looks great. So area is going to be integral from negative pi over 2 to pi over 2. Then we'll go 0 to 6 cosine theta. And then all we have is r d theta. No function. This is an area. If you added a function, then it would become a volume. Notice a few things, okay? I can double the integral and then just go from 0 to pi over 2 because of symmetry, right? So the area from 0 to pi over 2 is the same as the area from negative pi over 2 to 0. That's the only trick though. I can't do the whole like breaking it up thing because notice this upper limit is not a constant. So the shortcut I did in the last two problems does not apply. All the limits have to be constants for you to do it. But I mean, still, aren't we grateful? We can do 2 and then go 0 to pi over 2. No, you don't seem very grateful. Okay, 0, 6 cosine theta, r d theta. All right, so now, let's just hop to it. Antiderivative of r is going to be 1/2 r squared. And I'm evaluating that from 0 to 6 cosine theta. And then I still have d theta out there. This 2 cancels with the 1/2, does it not? Yes. And then we'll have now integral 0 to pi over 2. 6 cosine theta squared is 36 cosine squared theta, and then it's just minus 0, so d theta. And then what's next? As soon as you see cosine squared theta, little math robot should kick in and you go, oh, I replace that with 1/2 times 1 plus cosine 2 theta. Oh yeah, don't even hesitate. Don't sit around wondering. If you were to see sine squared in the near future, you would replace it with 1/2 times 1 minus cosine 2 theta. Burn these in your brain. If you forgot them from Calc 2, just put it in there somewhere safe for the end until the end of the semester, okay? Great. So 36 times 1/2, I'm going to just pull an 18 out here, 0 to pi over 2, and then I have 1 plus cosine 2 theta, d theta. We can do this. Antiderivative of 1 is just theta. Antiderivative of cosine 2 theta is going to be plus 1/2 sine 2 theta, 1/2 because of the 2 in front of the 2 theta, you know, from 0 to pi over 2. Let's see, so this is 18 times pi over 2 plus 1/2 times sine of 2 times pi over 2 is sine of pi, which is 0, minus 0 minus sine of 0 is 0. So what is this? 18 times pi over 2, 9 pi. Ooh, 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 so nice. Okay, that was fab. Let us move on to a little bit more spicy of an area problem. The area of the region inside r equals 6 sine theta and outside r equals 3. Okay. So we have two polar curves. I'm sure you can tell this is a circle centered on the y-axis. And then this is a circle centered at the origin. But they're going to intersect, and I need to draw a good graph so I could figure out the limits of integration for my region and whatnot. So let's find the intersection for these two curves. So we're going to set 6 sine theta equal to 3, which means sine theta is 1/2. When does that happen? Do you remember? Do you know your unit circle? At pi over 6 and 5 pi over 6. Okay, very good. So now let's draw the region whose area we're trying to compute here. Circle radius 3. So let me draw that one first. Actually, they both have radius 3, don't they? Copy, paste, and then the other one is sitting up here. Okay, very nice. So this one is 6 sine theta, the one centered on the y-axis. This is r equals 3. And then we want the region inside the upper circle, outside the lower circle. So we want this. Yes? Okay. And then conveniently, we already know this intersection happens at pi over 6. And over here, 5 pi over 6. Beautiful. So let's figure out the limits, yeah, for theta and r. So theta, well, maybe it's clear already, right? Theta goes from pi over 6 to 5 pi over 6. And then r, okay, watch this. This is where you're going to be so happy I showed you this trick. So start from the origin and then draw a line going through the integration region. Where it hits first is your lower limit. Where it hits next is your upper limit. Lower limit, upper limit. Who's this? The lower limit is r equals 3. Upper limit, who's this? 6 sine theta. Yay! Okay, now let's put it all together. So area equals integral pi over 6 to 5 pi over 6. Then we can go from 3 to 6 sine theta, and then you just have r dr d theta. No cute shortcuts, right? Because we have a theta here. It's a function. These are not all constants. Also, like, I can't cut it in half and put a 0 somewhere. I could go from pi over 6 to pi over 2 and then double it, but it's not like having pi over 2 is any more helpful than 5 pi over 6, in my opinion. I mean, if you want to change this to pi over 2 and put a 2 outside, knock yourself out. I don't think it's going to make life that much better. So just onward and upward. Let's go. So we have, and yeah, you got to rewrite everything. Ooh, pi over 6 to 5 pi over 6. Then we have antiderivative of r, which is 1/2 r squared. and then that gets evaluated from 3 to 6 sine theta, and then I still have this d theta out here. So let me take the 1/2 out. I like taking the constants out. It makes it a little easier on your brain to process kind of what's going on. 36 sine squared theta minus 9 d theta, right? Good. And then what did I tell you? This is if you go into robot mode. I see a sine squared. I'm going to immediately replace it with the half angle identity. So this is 36 times 1/2 times 1 minus cosine 2 theta, because it's sine, minus 9 d theta. And then we have 1/2 times the integral, pi over 6 to 5 pi over 6. This is 18 times 1 minus cosine 2 theta, right? So that's going to become 18 minus 18 cosine 2 theta minus 9 d theta. And then this just ends up being 9 minus 18 cosine 2 theta, right? Okay. So we have here, do we want to take a 9 out? I'm on the fence about it. Let's do it. So I'll have 9/2 out here. Pi, why was I on the fence? This is going to be fabulous. Okay, times 5 pi over 6. And then this is 1 minus 2 cosine 2 theta. Oh yeah, this is great. Okay, d theta. Good. 9/2. Antiderivative of 1 is just theta. Ooh, what about this? Whose derivative did you take to get negative 2 cosine 2 theta? It was a negative sine 2 theta. And then this goes from pi over 6 to 5 pi over 6. Ooh, this is a good one, especially if you have no calculator, like many of my students do. So 9/2. 5 pi over 6 minus sine of 2 times 5 pi over 6 is 5 pi over 3. We'll do this slowly. Minus pi over 6 minus sine of 2 times pi over 6, that's pi over 3. So what's going on? 9/2. 5 pi over 6 minus pi over 6, that's 4 pi over 6. Minus, let's see, sine of 5 pi over 3, that is in quadrant 4. So it's negative rad 3 over 2. So this is going to be plus rad 3 over 2. And then this ends up being plus sine of pi over 3, which is also rad 3 over 2. So what's going on? We have 9/2 times 2 pi over 3 plus rad 3. Okay. I don't know. What do we do with this? Distribute some more? Sure. Distribute. So the 2's will cancel. I have 9 pi over 3, which is just 3 pi plus 9 rad 3 over 2. That's it. How do you feel about that? I mean, it's not the cutest answer we've ever gotten. Now, is it? But it should be correct. Anyways, I hope you enjoyed the video. I think that's all I have for you lovely people. Yes. I was going to say, the other thing we went over in class this week was reversing the order on the limits of integration. So I was going to make a separate video on that topic because it's more something you do with rectangular. You could do it with polar, certainly. You certainly could, but I think I should just break that up and do it at a later time. Now, oh yeah, this answer is correct. That's what I was checking right now, checking my answer key. Okay, anyways, so that's coming next. If you have if you're in Calc 3 and there's certain lessons that you would like more videos on or examples for, just let me know, okay? You can email me or just comment down below. Also, subscribe if you haven't already. I checked my YouTube analytics. So many people who watch are not subscribed, and it helps my channel so much if you could just click that subscribe button. You can also follow me on Instagram and TikTok at Math TV with Professor V, and I'll be back soon. Love you guys.